Now that we've completed our design, the last step is to test our 4-bit comparator. To do this, we need to create a test bench. So let's see the steps in doing this. We start off with the keyword module and then a name for this module. Let's call it test-bit-comp4. Because this is our top level test bench, we don't have any connections, and we always conclude with an end module. Looking at our 4-bit comparator, we've got to provide a 4-bit input for A, another 4-bit input for B. And to do that, we'll create two reg variables of size 4, and let's call them in1 and in2. We'll use in1 to connect to A and in2 to connect to B. And we have a single bit output, which we will use to drive a wire. Let's declare a wire. It's a single bit, and let's call it greater than, as it represents the result of the comparison, indicating if A is greater than B. Our next step is to instantiate the module that we want to test. Our module is called bitcomp4. And let's give it an instance name. And then we need to make connections to the two input ports and to the output port for that module. So we do that using named port connections. So we've got A, B, and G. So for A, let's connect in 1 to A, in 2 to B, and greater than to G. And that's our module instantiation completed. And our next step then is to provide some values to test our design. And the simplest way to do this is with an initial construct. In our case, we want to group a number of statements as part of the initial, so we use a block, which is defined with a begin and end. Let's do one test to begin with, and we just pick a value for in1 and in2. So let's say in1 is 4 and in2 has the value 5. These values will be assigned to in1 and in2 at time 0. And let's say we want to do another test 10 time units later. We might want to change in2 to 3. So our first test will have A with the value 4 and B with the value 5. So the output should be 0 because 4 is not greater than 5. And for our second test at time 10, in2 will have the value 3 and in1 still holds the value 4. And in that case, 4 is greater than 3, so our output should be 1 for the second test. And we won't do any further testing for this particular test bench, but in practice you'll need to do more complete testing to verify the functionality of a design. One last step before we run this simulation, let's include the monitor task to view outputs. We print out the time at which monitor occurs, and then we provide a string with format specifiers. To format the output, let's just start with a tab and the string in1 and a format specifier %b, and let's have another format specifier. Let's print out the value in decimal. Let's do the same for in2, in binary, and in decimal. And our output greater than, and that's a single bit. What we have here, we've got 1, 2, 3, 4, 5 format specifiers. So we need to ensure that we supply 5 arguments corresponding to those 5 format specifiers. So one way to do it is to just line up the arguments in this way, in 1, So we're printing out in one twice, once in binary and once in decimal. In 2 we're printing out with this %b here and this %d here. So we need to specify in 2 twice as well. And finally we've got our greater than, and we print that out using this %b. I formatted it in this way so that for a given format specifier you can see the corresponding argument. In practice though, we normally just include all the arguments on the same line, so it normally looks like this. So let's save our test bench and let's compile it to check for any syntax errors. You can see with the check symbol here that it's compiled without any errors. In the transcript window, you'll also see a message indicating if the compilation is successful. Let's compile our design modules. They compiled successfully. And if we were to run this simulation, you can see what the output is using our monitor. You'll see the details of how to run a simulation in the lab, so I'll just quickly go through the steps here. To run the simulation, just go to Simulate, Start Simulation, click on Work, and scroll down to find Test bitcomp4. Select that and click OK. And when test bitcomp4 is loaded, it automatically loads the design modules that it needs, so bitcomp4 and bitcomp. And the final step then is to just run the simulation, so type run space -all. And if you examine the output, you'll see that it is correct. So 0 is the time, 0, 4 is our first value for in1, 5 is our first value for in2, and greater than is the output, which is 0. And then at time 10, we have these test values 4, 3, and greater than is 1. To summarize, we introduced vectors. Vectors allowed us to declare and use groups of bits. Vectors can be used with both wire and reg types. In addition to accessing the entire group of bits, it's possible to use bit access and bit part access when dealing with vectors. There are also ways to create groups of bits, and we did this using bus concatenation and bus replication. Constants in Verilog can be specified in a number of ways. We covered how to represent sized and unsized, unsigned constants using different bases in Verilog. Finally, a design example for a 4-bit unsigned comparator was developed using simple gates. While useful to illustrate the hierarchical design approach and the deployment of vectors, we will in future segments move away from gate-level descriptions and strive to develop designs using behavioral constructs that enable us to think about behavior and not low-level gates.